Dark matter silently sculpts every galaxy we see, and its hidden hand is behind the universe's grandest structures. Stay tuned, because number 1 reveals a cosmic secret almost nobody guesses, and you'll want to hear it all the way to the end. Imagine a universe where galaxies would drift apart like scattered islands, each isolated in the void. Dark matter provides the invisible gravitational glue that binds billions of stars into coherent structures, preventing them from scattering into emptiness. Observations of galaxy clusters show that the visible mass accounts for only a fraction of the total pull. The rest comes from a halo of dark matter that envelopes each system. Simulations that omit this hidden mass fail to reproduce the tight, rotating disks we see in reality. By anchoring galaxies together, dark matter sets the stage for all larger cosmic architecture. Next, we'll explore how this unseen force explains the puzzling speeds at the edges of spiral galaxies.
Consider the puzzling speeds at which the outer edges of spiral galaxies spin, moving far faster than the luminous matter alone should allow. Early measurements revealed flat rotation curves, a phenomenon that defied Newtonian expectations. Dark matter, forming an extensive halo around each galaxy, supplies the extra mass needed to keep those outer stars in orbit without flinging them into space. Researchers estimate that roughly 85% of a typical galaxy's mass is dark, a figure that aligns with the observed rotational stability. This discovery not only reshaped our understanding of galactic dynamics, but also sparked the modern hunt for the particle behind the mystery. Up next, we'll see how dark matter seeds the massive clusters that dominate the cosmic landscape.
Surprisingly, the first massive structures to emerge in the early universe were seeded by invisible dark matter clumps, acting as gravitational wells that attracted ordinary matter. As the cosmos expanded and cooled, these overdensities grew, pulling in gas that later ignited to form galaxies. Over billions of years, the galaxies congregated within the same dark matter halos, giving rise to the colossal clusters we observe today. Simulations such as the Millennium Run demonstrate that without dark matter's early scaffolding, the observed distribution of galaxy clusters would be far less pronounced. This hidden framework also explains why clusters appear to be more massive than the sum of their visible components. Coming up, we'll trace the delicate filaments that connect these clusters across the vast cosmic web.
Hidden within the vast emptiness, dark matter weaves a delicate network of filaments that thread together galaxy superclusters, forming the cosmic web. These filamentary strands, composed primarily of dark matter, serve as highways along which galaxies travel and merge, shaping the large-scale pattern of the universe. Observations from large surveys like the Sloan Digital Sky Survey map the luminous galaxies tracing these invisible threads, while gravitational lensing reveals the underlying dark matter distribution. The web's intricate geometry influences everything from galaxy spin alignment to the flow of intergalactic gas. Researchers estimate that over 80% of the universe's mass resides in this sprawling scaffold. Next, we'll discover how dark matter silently drives the dramatic collisions and mergers that reshape galaxies.
Few people know that dark matter's gravity acts like a silent conductor, orchestrating galaxy mergers that redefine cosmic neighborhoods. When two galaxies approach, their dark matter halos interpenetrate first, creating a deep combined potential well that draws the visible stars together over hundreds of millions of years. Simulations show that without this dark halo interaction, many observed merger remnants, such as elliptical galaxies, could not form in the observed time frames. The energy dissipated during these encounters also fuels bursts of star formation, lighting up the night sky with new stellar nurseries. Moreover, the merger rate itself provides clues about the amount and distribution of dark matter across epochs. Up next, we'll examine the faint imprints dark matter left on the oldest light we can see, the cosmic microwave background.
Gravitationally, dark matter left subtle fingerprints on the oldest light we can observe, the cosmic microwave background, CMB. Tiny temperature fluctuations in the CMB correspond to regions where dark matter was slightly denser, pulling in ordinary matter, and creating acoustic waves in the early plasma. Measurements from missions like Planck reveal a pattern of peaks and troughs that match predictions of a universe dominated by dark matter and dark energy. These anisotropies allow cosmologists to estimate that dark matter makes up roughly a quarter of the total energy density of the cosmos. By decoding these ancient ripples, scientists gain a window into how the invisible mass guided the formation of all later structures. Coming up, we'll see why dwarf galaxies act as a litmus test for dark matter's distribution.
When astronomers map the tiny dwarf galaxies that orbit larger systems, they uncover patterns that betray dark matter's hand. Dwarf galaxies are especially sensitive to the gravitational pull of surrounding dark matter halos, often residing in regions where the halo density is highest. Their unexpected abundance, or lack thereof, in certain locales, known as the missing satellites problem, has driven refinements in dark matter models, suggesting that warm or self-interacting dark matter could better explain the observations. Additionally, the spatial arrangement of dwarf galaxies around the Milky Way hints at planar structures that may reflect underlying dark matter filament orientations. Understanding these distributions helps fine-tune simulations of galaxy formation. Next, we'll explore how dark matter regulates the very birth of stars within galaxies.
Astrophysicists have discovered that dark matter halos regulate how quickly stars are born across the universe. A massive halo provides the deep gravitational well needed to retain gas, allowing it to cool, collapse, and ignite new stars. Conversely, in regions where the halo is less massive, gas can be expelled by supernova feedback, suppressing star formation. Observations show a correlation between halo mass and the star formation rate, known as the stellar-to-halo mass relation. This relationship helps explain why massive galaxies can sustain steady star formation while smaller ones often become quiescent. By shaping the availability of fuel, dark matter indirectly governs the luminous output of the cosmos. Up next, we'll look at how its mass bends light, giving us a powerful mapping tool.
In the early universe, dark matter's mass bends light, allowing us to map its invisible scaffolding through gravitational lensing. Massive clusters act as natural lenses, distorting and magnifying background galaxies in ways that directly trace the underlying mass distribution, most of which is dark. By analyzing lensing patterns, astronomers reconstruct detailed dark matter maps, revealing clumps and filaments that match simulation predictions. This technique has even uncovered dark matter concentrations with no associated visible galaxies, underscoring its dominance. Moreover, lensing measurements help refine estimates of dark matter's total amount and its interaction properties. Finally, we'll consider the grandest implication: how dark matter determines the universe's long-term destiny.
Finally, the biggest impact of dark matter lies in shaping the universe's long-term destiny and the grand architecture of cosmic structure. Its pervasive presence slows the expansion of space on large scales, counterbalancing the accelerating push of dark energy, and determines whether galaxy clusters remain bound or drift apart forever. Simulations suggest that if dark matter remains dominant, massive superclusters could persist as isolated islands in an ever-diluting cosmos, while smaller structures dissolve. The balance between dark matter's gravitational pull and dark energy's repulsive effect ultimately decides the fate of all cosmic formations. Understanding this interplay not only clarifies the present layout of the universe but also paints a picture of its future evolution, reminding us that the unseen mass continues to steer the grand narrative of everything we observe.
We've traveled from the subtle glue that holds galaxies together to the profound role dark matter plays in the universe's ultimate destiny, uncovering a tapestry woven by an invisible force. If you enjoyed this journey through the unseen, subscribe so you don't miss the next mind-blowing list that drops every week. Which dark matter effect amazed you most? Let me know in the comments below. And if this video sparked your curiosity, give it a like to support the channel. Thanks for watching, and keep looking up at the mysteries that shape our cosmos.